Hello and welcome back. So what about that series 1 over 2 to the n minus 1? How are we going to handle it if the comparison test doesn't work? Well, intuitively, when n is very large, the terms of 1 over 2 to the n minus 1 are acting a lot like the terms 1 over 2 to the n. They're basically the same when n is large, right? What's the difference between 2 to the n minus 1 and 2 to the n when n is like a million? Right? There's almost no difference at all. There's only a difference of 1, in fact. And so these terms of our series are acting a lot like the terms of the 1 over 2 to the n series, which we know is a convergent geometric series. So since that geometric series converges, our series should converge too. That's our intuition. But again, the problem is when we try to compare it to 1 over 2 to the n, the problem is that the inequality direction is not going the right way. It worked when there was a plus on the bottom, but now it doesn't work when there's a minus on the bottom. Because here now, we know that the series 1 over 2 to the n converges, but that doesn't say anything about the convergence or divergence of a bigger series. Maybe it's, not that big, not that much bigger, and maybe it still converges. Maybe it's too big and it diverges. You really can't tell when you have an inequality set up like this. So what to do? Thankfully, we have the limit comparison test to come to the rescue. The limit comparison test, which is abbreviated LCT, whoops, I just crossed it out. Apparently that does not highlight. Says this, suppose you have a sub n and b sub n are positive terms eventually, so for some little n bigger than or equal to big N. Here a sub n represents the terms of our series, the one that we want to find out about, the one that we don't really know about. And the b sub n's are the terms of some known series that we're trying to compare to, just like it was in the comparison test. Then what we're going to do is take the limit as n approaches infinity of a sub n over b sub n. This is why we had to have positive terms and not just non-negative terms. We can't allow for the b sub n's to be 0, otherwise you'd have a 0 in the bottom of the fraction. So we're going to take that limit as n approaches infinity of the a sub n's over the b sub n's, and if you get some positive number, so if you get 10 or pi or 1,000, then the convergence and divergence of the a sub n series and the b sub n series will be the same. So if the b sub n's converge, then the a sub n's have to converge as a series. If the b sub n series diverges, then the a sub n series has to diverge as well. What this is doing is it's saying, what's the comparison between the terms of these series? Remember when we were comparing something like 2 to the n with n to the third, and we said, take the limit as n approaches infinity of 2 to the n divided by n to the third? That'll compare the growth rates of those two expressions. And we saw that 2 to the n grew a lot faster than n cubed. Because the limit ended up being infinity. Well, if the limit that we get is some number, let's say 3, for example, well, that means that the a sub n's are 3 times as big as the b sub n's. But that's it. They're not growing faster. They're just always 3 times as big as the b sub n's, or eventually they're getting closer and closer to being 3 times as big as the b sub n's. And so when that happens, if the b sub n's as a series converge, well then the a sub n's have to converge as well. Just multiplying the terms of a convergent series by 3 is not going to change the convergence of that series. Similarly, if the b sub n series diverges, then the a sub n series, which is just 3 times the b sub n's, is going to diverge as well. If you take a divergent series and you multiply all the terms of that series by some number, it's not going to change the convergence or divergence, as long as it's not 0 that you're multiplying by, I guess. So that's what happens if the limit as n approaches infinity of a sub n over b sub n is equal to some positive number, a positive finite number, I should say. Infinity doesn't count as a number. The other two conditions are the other two conditions. So what happens if that limit is equal to 0? Or what happens if that limit is equal to positive infinity? Well, if the limit is equal to 0, that would say that the b sub n's are growing a lot faster than the a sub n's are, right? That's the only way that this fraction can be dragged down to 0, is if the b sub n's are growing at a faster rate than the a sub n's. And so if the b sub n as a series converges, then these smaller a sub n's as a series would have to converge as well. So in comparing them, we're comparing them by using this ratio, and instead of like an inequality. So if we get 0 here for this limit, that means the top numbers are going to be smaller than the bottom numbers eventually. A lot smaller than bottom numbers. And then the third condition, or third case, is that if we take that limit and we get infinity, well, that means that the a sub n's now are winning. They're getting bigger faster than the b sub n's are. And so if we know that the series of b sub n's diverge, then the series of a sub n's, which are bigger, is going to diverge as well. Let's look at how to use the limit comparison test in example 4. Here we're given the series 2n plus 1 over n plus 1 squared, and we're going to try to figure out, does that series converge or diverge? Now, one thing to note up here is that we'll always want to put, so before we get started with example 4, we'll always want to put our known series or the terms of the known series on the bottom. You can make other flavors of the limit comparison test and get around this, but I think when you're just starting out with the limit comparison test, it's nice to have a method that you always used as to kind of keep things stable. And if you always put the known series terms on the bottom, the b sub n's, again we said were like the known ones, that could be like a 1 over n or 1 over n factorial even, or something like that. Then it helps to keep things stable and standard and matching the way we've presented it here. Again, you could rewrite the limit comparison test differently, and once you really get to understand the concept, then you don't really have to follow these strict rules. You can compare them however you like, but as long as you understand how to use the results of that limit as n approaches infinity, then that will work. So, but for now, always put the known series terms on the bottom. All right, so for example 4, what we're going to think is this. What's for dinner tonight? No. What we're going to think is 2n plus 1 over n plus 1 squared. We're going to expand out the n plus 1 squared so we can see what the leading term is. Looks like the leading term on the bottom is n squared, and on the top it's 2n. So we're going to write the leading terms just like we would do in the comparison test, write those leading terms. But here, knowing that we can't really write an inequality going either direction, it's hard to know what happens when you subtract on the top and subtract on the bottom, because they're competing kind of forces. One's making the fraction bigger, one's making the fraction smaller. I guess in the other order that we presented it. So rather than writing an inequality direction, we're going to write a little squiggly line, so like a little tilde kind of thing. And what this represents is that these are almost the same for large n. When n gets large, the leading term overshadows all the rest of the terms on the top and then on the bottom separately. So these two fractions are almost the same for large n. You could try that. You could plug in a really big number into both of these fractions, and you're going to get roughly the same number out of each of these. Now this 2n over n squared simplifies down to 2 over n, and that's the series that we're going to make our comparison to. 2 over n is like 1 over n. It's just twice 1 over n. And since 1 over n as a series diverges, well, 2 over n is going to diverge as well. as we mentioned, just taking a series and multiplying all the terms by 2 doesn't change whether it converges or diverges. Let's write this. These are the b sub n's, and these are the a sub n's. Just so we have things a grounding. So we're going to write the a sub n's on top. I'm going to use the expanded version of the a sub n's, the one where we distributed out. And we're going to put 2 over n on the bottom. Those are the terms of the known series. Well, as a first step, we can, instead of dividing by 2 over n, we can multiply by n over 2. That would distribute to the top. And the 2 would distribute on the bottom. Then this is like an infinity over infinity situation. So we'll divide top and bottom by the leading term of the bottom, which is n squared. And then take our limit, and we get 2 over 2, which is 1. Oh, I'll write out 2 over 2, which is 1. There we go. So which case is this? If you said case number 1, that would be correct. And that's not just because we got a 1 here. It's because we got some finite positive number. Some finite positive number. 1 is like our c in the limit comparison test. So we're looking at case 1. So what we can say is, by the limit comparison test, since the series 2 over n diverges, being a p-series with an unfortunate p-value, we know that our series, and I'll write it the original way it was presented, also diverges. We already said it's by LCT, limit comparison test. So there we go. There's an example of the limit comparison test. Let's look at example 5 and see what's going on with that. Here again, we're going to think about lunch this time. No, we're going to think, what are the leading terms of the top and the bottom? Well, the top is the n ln n. The bottom is n squared. And by the way, when you're thinking about leading terms, you can think back to the beginning where we listed out which kinds of expressions grow faster than others. So if you have an n squared, that grows a lot faster than n does. So if you're thinking about leading terms, n squared would be chosen over n, if those were your only two choices. If you had an exponential term, well, that would be the one that would grow faster than any of these polynomial terms. Now, it's a pretty easy comparison for this one because it's like n ln n. Well, that's going to grow a lot faster than 1 because 1's not growing at all. But I just wanted to point that out. So we're going to write the little tilde here to say these ones are approximately the same value when n is really large. And then we'll simplify the n ln n over n squared. This simplifies down to ln n over n. Now, that's not really one of the series or the terms of the series that we really know about. So maybe we can look at this and think, okay, would this series converge or diverge? And maybe what else could we compare this series to? And it turns out that we could compare this series to 1 over n. The series 1 over n diverges, right? The sum of 1 over n diverges. That's a p-series with p equals 1. And the ln n over n terms are going to be bigger than the 1 over n terms, right? What's changing is if you think about the 1 on the top compared with ln n on the top, well, ln n is going to be bigger. Like the bottom is the same, the only difference is that you have an ln n on the top, and that's going to be bigger when n gets bigger. So overall, this ln n over n fraction is bigger than the 1 over n fraction, at least when n is past e, as long as n is greater than e. So 3 or bigger. But we're just interested in the long run anyway. So basically, what we can think is we can compare this function, or this terms of the series here, with 1 over n. That's going to be our b sub n in this case. We'll try comparing it to 1 over n. All right, so here we have the limit as n approaches infinity of 1 plus n ln n over n squared plus 5. Again, flip the fraction to the top, so we have n plus n squared ln n over n squared plus 5. Here we can divide top and bottom by n squared. That's the leading term on the bottom. So we would get 1 over n plus ln n over 1 plus 5 over n squared. So we're dividing the top and the bottom by n squared. Now if we look at this, the fractions go to 0, but the ln n term is going to blow up to infinity. It'll be kind of slow, as we mentioned, but it blows up to infinity. And the bottom is approaching 1, so overall this fraction is going to blow up to infinity. Which means that we're looking at case number, what here? Looks like case number 3. So what this is saying, and without even like looking at case number 3 and really memorizing this, you can just think, what's happening here? So you don't even have to write case number 3 if you don't want to. What you can think is, well, the top terms are going to be getting bigger faster than the bottom terms. So that means that if the bottom terms in a series diverge, well then our terms, which are bigger, they're growing they're growing faster than the bottom terms. That as a series would have to diverge as well because it's got bigger terms. So what we can say is by LCT, since the series, and I better write the n equals 2 to infinity, since the series 1 over n diverges, it's a p-series with p equals 1. The bigger series that we have in our hands, ln2, ln n, also diverges. There we go. Okay, so there's an example of case number 3. Let's look at example 6. Here, once again, we're going to think in our heads, or on paper. Oops. We're going to think, all right, what's the leading term on the top? Well, whoops, I don't want to say equals. That's going to be n squared the leading term on the bottom, well, it's going to be n to the 7th. Now it's still stuck in the radical, but it's the leading term, at least inside the radical. Try to write that a little bit better. Okay. And these are going to be approximately the same value when n is really large. So we can think those are approximately the same when n is really large. Now, what we could do is try to simplify this. So we have n squared over n to the 7 halves, which would be 1 over n to the 3 halves. You can think this will be n to the 2 minus 7 halves, which is negative 3 halves, and that would be 1 over n to the 3 halves. And this is the series that we want to compare to. So this is like these are like our b sub n's. I really should be writing these in red, actually. 1 over n to the 3 halves. These are our b sub n's here. Let's take the limit as n approaches infinity of R series. So R series will always go on top over this known series oops, I forgot to multiply n to the 3 halves up on the top. So this would be, if you multiply n squared times n to the 3 halves, that'll be n to the 4 halves plus 3 halves, that'll be 7 halves. And then plus 2n to the 5 halves. All right. Now, one thing that we're going to do is write the square root as a half power. I forgot I was going to do that. The reason is then it's a little bit easier to see what we're going to divide the top and the bottom by. This n to the 7th is really like an n to the 7 halves. Now we can't distribute the half power to each of these terms. We can't distribute exponent to cross addition. That only works for multiplication cross addition. But if we were to ignore this 3 right here, well, this would be like an n to the 7 halves down the bottom. So what we're going to do is we're going to divide the top and the bottom by that leading term of the bottom, which is the n to the 7 halves. And what this looks like is, let me take a little bit of this off to the side here. I'll do this in green. You know what, let's do the top first. So we have 1 plus 2 over n. So when we subtract those exponents, you'll get 2 over 2. So that'll be an n to the first power, and it's going to be on the bottom because there's more exponent on the bottom. Okay, and then trying to divide this bottom by n to the 7 halves, let's do that work on the side. I'm going to write n to the 7 halves as n to the 7 to the half power. Now we can see that we can bring this all into a single half power. It's going to be 3 plus n to the 7 over n to the 7. But that we can write as 3 over n to the 7 plus 1 to the 1/2. So we're sneaking in the n to the 7 halves by rewriting it as n to the 7th to the half power, so that our powers are both the same, and that way we can divide the n to the 7th into the other part, into the 3 plus n to the 7th. So that helps simplify and write things as fractions, because all those little fractions go to 0. And we end up getting 1. So which case is that? You said case 1. then that's correct. And again, that's not just because we got a 1. A lot of times you will get this 1 if you do this same kind of analysis here, because all we did is we looked at the leading terms, and when you do that kind of analysis, when you take the ratio of the terms that we started with the terms of a known series, these two are going to be apart by a multiple of 1. Basically, they're the same value when n gets really large, so they're not even a multiple of like 2 or 5 apart. They're almost the identical same value. That was a little redundant. Identical same. Okay. So we can say then by the limit comparison test, since the series 1 over n to the 3 halves, what does it do? Does it converge or diverge? If you said converges, that would be correct. This is a P series. P equals 3 halves. I'll just write the 3 halves, not write the greater than 1. Then the R series that we're interested in. Again, I'm intentionally not writing the n equals 1 to infinity because you can assume that n starts from 1 and goes to infinity if you don't write it here. But don't get too lazy about that. If you do have a different n, write it out. If n starts at 2, you got to write n equals 2 to infinity. So R series is also going to converge, because case 1 says that the convergence and divergence are tied together if you get the limit equals some positive finite number. In our case, it was 1. This was like our C value again. Okay, so that was the comparison test and then the limit comparison test in this video. Thanks so much for watching, and see you next time.